Good morning, ladies and gentlemen. Today we're looking at data transformations. And data transformations start by asking the question, what do we do when the data isn't linear? So let's take a look at a very basic example. Time and rabbits. So time in months starts off with 2 rabbits, they breed, I made up the numbers to show a point. And let's see what this data looks like on the calculator and on a scatter plot. Alright, so that's the data set up. Time on the x-axis, rabbits on the y. And the scatter plot looks something like that. Now, you can see there might be a little bit of a curve in the dots, but it doesn't look too bad, does it? You're like, well, it's not far off linear. So let's see what difference that actually makes. The question we're going to ask is, let's predict the rabbit population at 14 months. Alright, now this is extrapolation, so it might not be entirely reliable, but if we look at the graph, and we go across to 14 months, and then we head up to where the curve might be going, so we could sort of imagine the curve going up here. Oh, we'd expect 190, close to 200. Alright, so let's try our prediction with a straight line. Menu, analyze, regression, show linear. Alright, so we've got this straight line through the points. And the points that don't look far off it, so it doesn't look bad on the first instance. But now let's see what the prediction comes out to. At 14 months, it will be about 130. Alright, let's do some maths to verify that. So our equation is that. And to make the substitution, we will go rabbits is equal to negative 22.4 plus 11.42 multiplied by, I'm just going to use that as a multiplied by, instead of time, we're going to substitute in 14 months. Note how in the equation above I've written it in terms of words, not x and y. That's what we expect in further, in terms of words, the variables, then the substitution, and then after the substitution has been made, we can see that there will be 137 rabbits. Alright. But the issue comes when we look at this data and recognize that actually we were expecting something around 190, 200, so something's gone wrong here. And what's gone wrong is that there is quite a strong pattern in the residuals. So there are residuals, and there's clearly a pattern there. And what that means is that this line here, as a linear, is not appropriate. Simply that the data is not in a straight line, so why put a straight line through it? Two options here. Either we can put a curved line through it, or we can make the data into a straight line, and then put a straight line through it. Now, in further, we like dealing with straight lines. Y equals a plus bx is a nice equation to work with. So what we do is we transform the data to make it linear. We linearize the data. Now this is where it gets a little complex. What we're going to do is imagine the curve of our points looks like this. So they're curving up. If we take all of the x values and square them, it has the effect of stretching them out horizontally. So for example, if this x value here was x equals 1, and we square it, well, 1 squared is just equal to 1, so that's not very exciting. So this next one across here was x equals 3. 3 squared is 9, so it moves a little. First one doesn't move a lot, second one moves, third one moves a little. Second one would obviously go to 4. This last one here, this middle one here, I hope you can see what my cursor is indicating. If we square that, it goes from 4 to 16. There's a jump of 12 there. And the last one, 5 squared, jumps 20. So you can see our jump is nothing, 6, 12, 20. As we go up, as we go further and further along the x-axis, the jumps get larger and larger. And what this does is has the effect of stretching those points out onto a straight line. So let's look at how we would do this on our calculator. What we would do is we go to our calculator. We'll get rid of that line. Go here. So what we're going to do is we want to stretch the x-axis. The x-axis is time. Time squared. So write t skew, or something to remind you that you're squaring time. And then what we're going to do here is write equals time, that's this column here, to the power of 2. And what it does is just taken time and squared it. Easy enough? Alright, now let's look at how that changes when we plot it on a scatter plot. So we go to our scatter plot. We don't want our x-axis to be time, we now want it to be time squared. And look at the data linearize. So, see that again, replay, action replay. That's the original data. And there's a clear pattern there. When we square the data, it looks like this, straight line. Now, let's put a straight line through that. Pretty good. Some above, some below. We can imagine the residual plot would be nice. Alright, how do we use that equation, so that equation there, to make a prediction? Well, let me just grab that equation there. Ooh, it's not going to work. Doesn't matter, I have it here. That's this equation. Now the key part here is squared. So you see previously on the calculator, it was 0.025 plus 1.04x. However, here, the x is referring to this axis. Now, this axis, we've squared. So instead of just calling it x, we remember actually we've squared it. So instead of, in this equation here, we just refer to this as x, we call it x squared. So here, our equation is rabbit population is equal to 0.25 plus 1.04 times x squared, or time squared. Now, if we want to make our prediction at the 14-month stage, well, that's rabbit pop will be equal to 0.25 plus 1.04 multiplied by 14 squared. Sorry, I'll do that in equation mode so you can see it. 0.25 times 1.04, that was bad, plus 1.04 So note, we've just replaced the time and substituted in 14. And if we put this here into our calculators, it will come out with this, 204 rabbits. Now, that's a lot of rabbits, but remember, when we were looking at the original data, so to convert this back to the original data, when we're looking at the original data and we wanted to look at what it would be like for 14 months, we were saying, well, this curve looks like it might continue and be up here by the time we get to the 14 months, which is around the 207. So, by linearizing the data, using a x-squared transformation, we've made our prediction far, far better, far, far more accurate. Alright, now, is squaring the x term the only way to linearize data? No, there's not. There's lots of them. In fact, in every circumstance, there'll be more than one option. So let's look at some other transformations. I might come back to that in a sec. Alright, so quadratic transformations stretch the values. So you can see what we just did was we squared the x values. And squaring the x values increases all the x values, but it increases the high ones more, which will stretch them onto a line. We could, once again, square the x values. The low ones don't move much, the high ones get stretched onto a line. Or the other option would be to square the y values. Now, squaring the y values has the same effect, but on the y values. The low y values barely move, because low numbers squared don't move much. But the high y values squared move a lot. Same again, high y values squared move a lot. Now, I realise there's lots here, and wait, there's more coming, but there's a nice tool at the end we use for knowing how to transform or which transformation to use. Alright, quadratic transformations stretch values. Log transformations. Log is where we take the log of a number. And you might remember from univariate data where we took the log of a large number and converted it into a small number. So log of 1,000 is 3, log of 100 is 2. The difference between 100 and 1,000 is huge. The difference between 2 and 3 isn't. We've essentially compressed down the 1,000 and 100 until they're quite similar. So using a log has the effect of compressing the x values, pulling them back this way. Same with 1 on x. I might take a second to explain 1 on x. So if we wanted to use what's called a reciprocal transformation, 1 on x, that would be like saying, well, 1 divided by 1 is equal to 1. That hasn't changed much. 1 divided by 2 is equal to a half. So an x value of 2, when transformed, becomes a half. An x value of 4 becomes a quarter. An x value of 50 becomes 0.02. So taking reciprocal transformations shrinks it back, in the same way log transformations do. Compressing the x, compressing the x, compressing the y, compressing the y. Good things to know what your calculator is going to do. Now, fortunately, the textbook and BCE published this. So this is called the circle of transformations. If the data is curved like this, any of these transformations will work. So note how with y squared they're suggesting, well, we stretch the y values up, and that will make it towards a y value. The other options are shrinking the x values. So here, the other option was log x. Log x and the reciprocal of x would have the effect of doing that to the x values, the extreme x values, bringing the curve back into line. Transformations here, stretch y, stretch x, etc. Now, this means there's always more than one possible option. Typical questions might ask you to view a scatter plot like that, and then give you a multiple choice of which transformations could possibly work. They might say, would log x work, would log y work, would 1 on y work, or would x squared work? And you'd have to say, well, x squared is the only one that will work because it's the only one that applies to that type there. Or, if you're asked to do a trial transformation, the question will tell you which one of the possible two to use. Alright, so examples on how to use this are in the next video. That's some of the logic of transforming the data. We take a curved data, make it straight, then use the straight line equation but in a modified form to make our predictions. Examples are in the next video, so please watch it quickly after this one or you'll forget the theory and the examples won't make any sense. Thank you very much.